Alright, what we want to do is present to you a process called vector subtraction, and also talk about how that applies to acceleration in the case of uniform circular motion. So what we want to first do is think back to motion in 1D, because we were inadvertently doing vector subtraction without really saying that we did. So if I were to represent an object's motion with a velocity vector, let's say v1, and then maybe sometime later it's moving with a velocity v2, a larger velocity to the right. This object has clearly gained speed, and if I were to attach numbers to this, let's say this is 5 meters per second and then this is 10 meters per second, our object has clearly sped up. And if this were, let's say, in a time of 2 seconds, what we used to do was we used to numerically calculate the acceleration. We would just say, well, acceleration is final velocity minus initial velocity over time. So in this case it would be 10 minus 5 over a time of 2. So I guess that would be 2.5 meters per second squared. And by the way, that's a positive number. So we know that the direction of the acceleration is to the right. So what we didn't really tell you here was that this operation right here was a mathematical form of vector subtraction. But we actually want to focus more on, let's say, the graphical form of vector subtraction. So we've always seen how we add two vectors together. If I see that I had two vectors together, it was just tip-to-tail method, and you would draw one after the other, and then, if they were in different dimensions, you might do Pythagorean theorem in order to figure out how they add up. But we need to subtract v1 from v2 here, or vf from vi from vf. So in order to do that graphically, we got to get creative. So what we need to do is we need to say, okay, v2 is this vector. I'm just going to draw it as it is. It's that big. v1, I want to subtract this vector from here. And in order to do that, basically what we're going to do is vector addition. So I need to say, what is this vector negative v1? That would just be that in the opposite direction. So I'm going to draw it to the appropriate length and in that direction there. And basically what I want is I want to get the vector subtraction between v2 and v1 by saying I'm going to take v2 and add negative v1 to that. So when I do that, v2 plus negative v1 graphically, I would say, okay, let's draw v2. And then let's draw negative v1 right after that. So we're technically what we're doing is a form of vector addition here. And then if I did tip-to-tail method here, I start here, I end here. This is my vector v2 minus v1, or v2 plus negative v1. We could also call that delta v. And if you take a look here, numerically, this is worth 10. This is negative 5, so we're adding 10 to negative 5, and we get a delta v of 5 if you look at the length of it. So that makes sense with this right here, because what we have is a difference of 5. So when we're looking at our vector subtraction in one dimension, all we have to do is do this graphical technique, and it will make perfect sense as to why delta v is pointed that way. Now when you get delta v, that actually points in the same direction as a, because a is delta v over t. So you expect this sign and this sign to match, which means that this thing's acceleration is directed to the right. So the whole point of vector subtraction in this case is to get the direction of our acceleration. Now I can just show you maybe another example of doing that in one dimension. If we had something possibly slowing down, it's initially going this speed, then it's going this speed. So if I wanted to do v2 minus v1, well, we're going to draw v2 as it is. v1, the opposite of that, would be drawn to this length and pointed that way. And then we draw them one after another. I start out, I draw v2, and then I'm going to add it to negative v1. That's how we do vector subtraction. And so now we can do tip-to-tail method here. I start here, I end here. This is my vector v2 minus v1, or we could also call that vector delta v. It's pointed to the left, which tells me that the acceleration must have been to the left as well. So when my velocity is directed to the right, my acceleration is directed to the left, I get something slowing down. So this process is going to get our direction of our acceleration. Now we want to apply this to circular motion. So what we're going to do is take a look at that circular path. And I can draw some velocity vectors here. Draw one that way. I'm going to draw another that way. And I'm going to draw them all the same length because we want them to be going the same speed essentially. And I'm going to do some in between too. Now if you have a ruler, this is actually end up being a lot easier because you can easily draw them to scale. But what I'm going to do is I'm going to call this vector right here, let's call this V1, let's call this V2, let's call this V3. Let's do V2 minus V1. Let's figure that one out. So I need to draw V2 on its own. Replicate that vector right there. Looks like that. And then I need to draw negative V1, which is initially to the right, but when we make it negative V1, it's to the left. I get a vector like that. So when I try to do these vectors one after another, I'm going to draw V2, and then I'm going to draw negative V1. It looks like that. And I'm going to get my delta V vector here. My delta V vector is I start here and here. V2 plus negative V1 is that, or I'm just going to call it delta V in this case. That gives me the direction of my acceleration. So if I was looking at where this thing is accelerating when it's at this point in the circle, it is straight towards the center like that. Now we could probably do this with two other adjacent vectors. We do it with V3 and V2 as well. So let's keep those handy. Maybe I could do it in here. I think I have enough space. If I wanted to do V3 minus V2, I'm going to draw V3 just as it is. And then minus V2 would look like that, 180 degrees opposite. And so I'm going to draw V3 first, and then I'm going to add negative V2 to that. So here's V3, and then if I do negative V2, it will probably look like that. And then let's take a look at delta V now. Pointed directly to the left. Well, that gives me an acceleration that way. What you're always going to find is you can do this process with any two adjacent vectors, and your acceleration should be directed towards the center. So your velocity is always tangent, and your acceleration is directed towards your center. Now, some people look at this and they go, I don't quite understand why there's acceleration. You said we were moving at constant velocity. However, velocity is defined by both magnitude and direction. So essentially, what we're going to look at is the fact that this velocity is changing direction. If it's changing direction, it is undergoing a significant change, and that is because the acceleration is causing that change in direction. So essentially we have this term called centripetal acceleration. The name of it gives away the direction. It's always directed towards the center of your circular path, and if you want to solve for it, it is v squared over r. And keep in mind that v is equal to 2 pi r over t, capital T that is. When you look at these units here, you get something that's meters squared per second squared, but then you multiply it by meters, divided by meters. So that would be in the denominator. You get meters per second squared, and that matches the unit that we would expect for acceleration. Some people look at this and they think, well, maybe this is inversely related to r. You got to be careful here, because if we put that in for v, we can get it in terms of r and t. So if I put in 2 pi r over t, square it, and then divide by r, that would be 4 pi squared r squared over t, and then divide by r. What ends up happening is that it's actually not inversely related to r in uniform circular motion. So you get 4 pi squared r over t. So you got to be careful. A is v squared over r, but since v depends upon r and t, if you're looking for relationships there, you got to be mindful of that as well. So it's pretty easy to calculate a, and what you're going to see is that, well, if the size of v is not changing, the size of a is not changing. What's changing in all of these problems is direction. We see the direction of the velocity changing, we see the direction of the acceleration changing.